this talk is titled Many and Any, and we will shortly get to see what that's all about. But my keyboard is not responding to my slides, so here we go. I'm Alisdair Meredith. I work at Bloomberg for my day job, and I'm a former library working group chair for the ISO C++ committee, which means I've had something of an inside track on any of the library work for the last decade or two, which is how we end up talking about standard any at ACCU this year. And just for the reference, that's me busily consuming bugs. I'm not sure this is my best bug tracking solution, but when you want to push out the experimental limits, sometimes you have to try these things. I don't recommend that one in hindsight. The grasshopper's one which tastier. So, what is this session about? We have a quick introduction to describe what the type I'm going to be discussing is, the any type. And then we're going to have a slight diversion into some of the basics about test-driven development. The goal of this session is this is not an advanced session where I assume everyone knows everything about, what we be, about the typical goings on of an ACCU conference, which is aiming to be a bit more of an introductory level. So I'll just cover a little bit of the basics and why I'm talking about that in this session. Then we're going to implement our first implementation of standard any. I'm pointing at the screen. I have no pointer. This is wonderful. Sorry. Up early in the morning, not always great for my flow of consciousness being interrupted by my brain. Anyway, then we're going to take a look at some alternative approaches that can, different ways you can design and implement your standard any. Then we're going to have a look, just a quick look at how these things may combine to produce a wide variety of different possible implementations, leading on to some of the non-standard extensions I've been contemplating, some notes about my experience with that. The end goal of this, to go through all this, was to try all these different implementations and then try and benchmark them to understand the relationship between the trade-offs of the different designs. I'll give you a spoiler up front. I do not have benchmarking results. I got lost and buried in trying to do this and didn't emerge at the far end in time for this talk. But we will discuss the kinds of concerns I was looking at. And then we have the final summary of what did we learn out of all this. So a quick brief history of whatever this anything is. It was first published by our very own Kevin Henney in the C++ Report magazine, July-August 2000, under an article called Value Conversions, and was shortly thereafter donated to Boost, which was still in its, just after its inception phase, I think, but still in the very, very early days of Boost, around about 2001. So the topic we're looking at is just over 20 years old and was implemented originally in C++ 03, so it doesn't require all sorts of fancy modern shenanigans to implement this. In terms of standardization, well, we took quite the detour through C++ 11, and so it took quite a while before we could get around to looking at this again, but we finally shipped a standardized version in the library fundamentals technical specification, which is where we do the experimental features we would like to land into future standard libraries. And that shipped in 2015 and was deemed successful enough that it actually landed immediately in the following standard, which was C++ 17. And that forms the basis of what we'll be looking at today. So what is the any type? Well, it's a type that can hold anything, for some notion of anything, as long as the thing that you're trying to store can be copied. And again, the any object itself can be copied with whatever it's holding. What you can't store are reference types. References are not copyable in this notion. Function types, though if you try to store a function, your function will decay to a function pointer. And you can store function pointers. So can you store functions? Maybe, maybe not. Depends how much of a rules lawyer you want to be. And finally, you can't store arrays, which is also unfortunate. Arrays are a perfectly reasonable copyable type. But as we'll see as we go through, there's some specific issues in the interface that cause problems for storing arrays that will look like they work, but they're not going to do what you want in all likelihood. I said that the other key restriction is that the stored object must be copy constructible, because the idea of storing your object in the any wrapper is that the any wrapper is going to make a copy of it. And because the any object itself wants to be copyable, a move-only type is not good enough, because we know that there's going to be operations such as copying the any object that cannot be supported by such a type. Why is the any type an interesting thing to look at in the first place? Well, it's interesting because any is a regular class, not a class template. And I'm saying regular class, that's going to fire off some buzzwords of folks who think, regular objects and types have a specific set of meanings. I just mean it's a spread class in C++. And in particular, any is not equality comparable, because if any is holding two different types, what does it mean to try to compare them? So rather than trying to invent some strange semantics there, no, you can handle comparisons however you want by taking querying the public interface of the any, but we're not going to implement that for you. So any is a regular class, but in order to work its magic, it's going to rely on member function templates. Because obviously we're going to interact with an open set of types, whatever you want to put in there, templates are going to be involved. But because the any type itself as the wrapper is not a template, it's a great vocabulary type when you want to pass things through APIs. You don't want to make all these API layers themselves into templates. Any is a great leveler to say, okay, I'm passing things through in this type erased manner, as we like to say, where the type has fallen out of the type system as you communicate through the APIs and is unpacked again at the other side. So another way to think about it is it might be thought of as a smart pointer for void star, which is the traditional way that we used to anonymously pass types through the system. You would pass the pointer to the object, but then you're in trouble as to who owns the object and trying to track all the memory lifetimes. So any is like the smart pointer where it owns its copy, and it's just passable through APIs as void star was. So it's a nice C++ type-safe solution for passing types through the objects through the type system while not paying for the overhead for all the different types in your APIs. And coming around to the other part of this, so at the start of the talk, we're going to take a basic look at some of the notions of test-driven development. Basic idea, if you take it to as its most extreme, is you write your tests before you implement your code. And one of the big reasons for this is because you want to see the test fail, you know the test is working. And therefore, if your implementation that follows up is broken, you're going to see those errors. You know that the test is reliable. At least reliable to report errors, not successes. That's where you go after that. It supports incremental development, where you implement the test, you implement the feature. So it's a nice step-by-step approach. And by iterating with always a working system at each time, you grow out and intuitively you're going to get test coverage, because you don't get to implement a feature until it's tested. So as you're evolving your system, you're always in a good position if you want to refactor or change or clean up your code. You have the existing test suite, and as long as you're not changing your interfaces, other than adding features, the system stays stable. So it's in the sense of the always shippable, apart from the fact that until you've reached your shippable state, you're not really shippable, but you're always in a good stable state when you're trying to add and work with new features in the system. And as I say, you've got that test coverage. Key thing for me with this is when you check your code into source control, you don't check in with the failing test, because if you ever want to do something like a git bisect to try to find where errors are introduced into the system, you don't want those failing tests in your in your main branch. So the notion is you write the test, it fails, you update the component, it now passes. Now you've got a good checkpoint to check in, yes, I implemented this test, this feature now works. Next checkpoint in your source control. So other benefits, I said we get the test coverage, gives you the confidence in the code. The test coverage also gives you the confidence to refactor early and often. And what we're going to be seeing partway through this talk is that in as much as refactoring, you can almost completely re-implement the design behind the scenes because you've already got your test coverage against the interface, as long as you've not plumbed too deliberately down into implementation details that are not part of the interface, but things you can see and query about. Which is where we come to the notion that you design your interfaces for testing. So if your public interface exposes in the design everything you need for testing, you shouldn't be going out of your way to plumb into those crazy corner case steps, because if your contract doesn't address them, you don't need to do them. Otherwise, your public interface is out there, your public API is out there, you have the contract, so you're going to be testing it anyway. And by focusing on the actual use cases you have to introduce features, you avoid getting into that design creep where you have the premature generalization, where your object is all things to all people. And you just get lost in your design, and you now end up doing an awful lot of redundant work that's never actually used because the use cases to back it up turned out not to be there. Building up from your known minimal set of features, you'll end up with possibly avoiding a bunch of redundant work. And on the flip side, and the other big benefit, the main reason I went into this notion of TDD, incremental coding by style in bite-sized snippets is great when you're trying to present a talk in 90 minutes or less. So some of the risks I perceive when you're taking the test-driven development approach is by focusing on the immediate feature, you miss the larger scale architecture, and you might pull yourself into a direction that is not going to be good in the bigger picture once you have all the different parts working. Time spent on some of these redundant features as you're navigating through to the larger, more complete feature might end up doing, again, a bunch of redundant work as you do lead to continual refactoring. But again, being in a habit of refactoring, it's good. It's a good reflex and coding muscle to have, because it's going to keep your code clean and maintainable and readable and clear to folks coming to try to see what you did here at a later date. The main problem I have with TDD versus implement and then test is, given you're leading the testing, it can be difficult to know when you are complete. Have you got all the features? Have you covered all the corner cases? Or did you just cover the things that you thought to test because you didn't have a full test plan from the outset? So again, there's ways and means to address all these different risks. This is just my quick 5 minutes on TDD before we get into doing the whole incremental. This is a nice way to try to implement a simple standard library type. So the goals of this session: I'm going to provide a simple implementation of standard any, the simplest possible implementation, the easiest one I can imagine, using the test-driven development theme. Once I've got that working, I'm going to investigate some different design options that I can then run through my design, my test harness, and I'm looking at different ways I might be able to try to optimize different aspects of the design. Once I'm through with all that, I'm going to look at some potential extensions I was thinking of that we could bring to standard any if we wanted to do more work there in the future. I have no news that WG21, the ISO working group, would be at all interested in any of these extensions, but it's half the joy of implementing standard library features is you get to play around and have a better sense of the design space once you come out the other end. As I say, the goal was to have some benchmarking, to have an intuition of how the different aspects of the design played off. I'm going to talk about some of the things I was thinking there, but I don't actually have results to share, I'm afraid. So again, heads up. So moving on, my first any implementation, with the notion being test first, then implement, and repeat until we actually have a full implementation. So before we get going, we should probably figure out what the interface of any actually is. So this is my quick copy paste from the standard, and I eliminated some of the parts that I was less interested in just to try to keep it small and manageable within the session. There's something close to the C++ 03 version. So what we don't have here is the ability to emplace objects into your any, where you can pass a tag and say, use all these arguments and pass them to a constructor. This is just simple. You put values in and out, but compared to the C++ 03 version, I have added the move semantic support because that would clearly be useful and it has impacts on the design. The parts that are missing are almost redundant with everything you have here. They just save a couple of save doing all the constructing outside and passing and trying to move things through. So extra complexity for no value in the terms of this talk. So let's walk through the interface. First of all, we're going to have the default constructor, which will be constexpr, the copy constructor, and the move constructor, just as you would expect on standard type, on any typical value-like type. The default constructor and move constructor will be no except for hopefully obvious reasons. Certainly the move operations you want to be no except because large parts of those semantics rely on knowing that moves don't throw. Otherwise, the optimization doesn't do what people are relying on it to do. Then we have the value constructor where you pass in whatever kind of object you want to store. Obviously, this constructor is now a template because if I can pass any type in, the only way I can do that and capture that type information is to pass it in as a template parameter. And the key thing to notice here, which I suspect many in this audience will understand already, is that by passing T ampersand in a deduction context to a constructor like this, this is not an R value reference, this is a forwarding reference, where the type is going to be deduced from the call site to be either an L value or an R value, and that notion of L versus R value will be preserved. And we'll talk more about that again as we start implementing that particular constructor. And obviously we're going to have a destructor because when the object is destroyed, we need to make sure that we destroy whatever the held object is as well. Other typical parts of your public interface, following a classic rule of 6 kind of notions, you've got the assignment operators. We've got the copy assignment and the move assignment. And again, the move assignment is no except. And again, we have the ability to assign from any other type to replace the existing object with an object of a completely different type, or maybe another object of the same type. The other modifiers this type supports are a reset operation to clear out the state and destroy whatever the stored object is, and to swap two objects efficiently in a way that they don't throw exceptions. And our two observers. We've got a function that tells us whether or not the any object holds a value, and something that can tell us what type that stored value has. As for how we actually get the value itself out of the any, we will look at that further through the presentation. So, to start the presentation, the first thing we have to do with our test-driven development is test. So, here's my opening test driver. Pretty simple, not quite as simple as can be because I'm actually making a copy of my default constructed any. So any true TDD zealot will be slapping my wrist and saying, no, I've done 2 steps here, not 1. But for the sake of getting this talk and making progress, it just seemed propitious to have, it's a nice, simple, basic facility to start. This program will compile and run and has no errors. Wonderful. So, moving on, I don't want to actually be testing standard any other than as an oracle to tell me whether my own implementation is working as well as the standards implementation does. So, I'm going to implement all my tests in my namespace AJM. which happens to be my initials. Please don't go using this namespace because I'm already polluting it with many contradictory different packages at different times. But yes, that's my working place. And I would define a macro that I can pass on the command line that says, I want to test my version. Otherwise, my test driver is going to default to testing the standard version. So I can now define that. I can now run this test driver. And, sorry, going back a slide, this compiles fine because I've not defined test AJM. I define test AJM on the command line and boom, immediately the compiler tells me, I have no idea what AJM any is. My test is failing. Great, let's fix it. I'm going to make sure I include my actual header where I define my code that will implement AJM any. And otherwise, I can do the same thing for the standard. And having just sorted out which particular version of any we want to use, you'll notice I'm doing something people will frown upon maybe. Having a CPP file with the main. The code's not going to be confused with anything in the outside world. I'm very specifically writing a test driver. So yes, I'm just importing the any type I wish to test into the global namespace and testing it as a global name. If I'm being super strict, I can probably create scenarios where that would cause problems, but it's not going to arise when I'm just doing a simple implementation testing that my facility works. And I can now switch between standard and my implementation on a whim, just to make sure everything's working correctly. So, are we good now? No, I've actually not done the implementation yet. So, any.hpp does not yet exist. Let's create it. Here is my super simple implementation of any. I don't think this is going to stand up to much scrutiny, but I think it's going to get me past my first test driver. Indeed, that simple empty aggregate will indeed pass this very simple test. Yay, we've got our first success at our second attempt at the test driver. That now means we need to start adding more tests with the repeat, to say, okay, what's next? Well, I said any could store anything. So let's store an integer in there and make a copy of that. Works great with the standard version. How about mine? Well, looks like I'm actually going to have to put something into that anybody now. So what's the least I can get away with? Well, I know this chapter will be default constructible, and as soon as I add another constructor, the default constructor is going to start failing. But I do need to have that forwarded constructor that can take anything. So, yeah, this should now get me past onto working on my next feature. So let's increase the test a little bit. I'll have that default constructor. I'll make my copy A5, and I'll then make a copy of the Y object and assert that each appropriately does or does not have a value, which is enriching my test condition. Oh, has value. I better go and implement that then. So that's the test. We now provide the implementation to pass that test. It tells me whether or not I did indeed store an object in this any. I'm using default member initializers to, if I don't provide anything in my constructor to say what the and the has value is, it will always default to false. And if I call the constructor that takes an argument, well, has value better be true because we've just given it a value. And we now have the has value function to query it. And I think I missed a couple of slides. That's quite deliberately not const qualified, so I could have that test go on and complain that I didn't put the const in there. In hindsight, just as I'm here now, I realize I've missed those slides. So errors in the slide, folks. I didn't actually test that has value is const qualified as it should be. So we do the implementation. In practice, I'm going to skip a little bit just to keep the talk focused, because if we keep going at this absolute slow pace we've been looking at, it will take 2 or 3 seconds just to get through there. So we know that in practice, we're going to have to store the value that's applied to us. There's no space for it in the object itself. It's going to have to go up on the heap because these types can be arbitrarily large. So we have a void star data member that can then, when I have an object, I will allocate that object onto the heap with new, and that now serves to make sure that I'm now storing my object as opposed to just saying, you gave me an object and I threw it away. So we moved it a little bit ahead. And we hit the interesting issue that this already fails, because that perfect forwarding constructor, if I go back to the test case here, if you look at the any z being passed a y, the y is a non-const L value. Well, that perfect forwarding constructor says I'm an exact match for that, whereas the implicitly declared copy constructor that we've not yet dealt with has a const tref. So our perfectly forwarding constructor here is actually the better match. So now I'm going to try and make a new any by forwarding my any object there, which will in turn try to make a new any by forwarding my object there, and you see the infinite recursion here, I hope. This is going to crash when I try to run it. This is not good. And indeed, I don't have that's what my test showed, it went bang. So what we're going to use a C++20 feature just because it's the easiest way to express this. There were all sorts of ugly hacks and ways you could do this in earlier versions of the language. But what we're going to do is we're going to ensure that if we remove any CD, const, volatile, and reference qualifiers from the object being passed, when we deduce T is either going to be, if I'm passed an R value, T will be that type. It will not be reference qualified. It will just be that type. But if T is an L value, so if the argument I passed is an L value, then T will be deduced to be an L value reference. This is how the forwarding references work. This is one of those wonderful issues that confuses people as they're trying to understand this for the longest time. But understanding that simply either T could be an L value reference, which is what's happening when we pass Y to that constructor. So what we want to do, we want to strip all the references and CD qualifiers and say, if after I've stripped all the references,
Howard Hinnant or James Lupton.
Sorry, my phone Siri decided to be super helpful, even though it's not supposed to be quiet there. So we say, are you the same type as any, the type I'm actually trying to implement? Because if you are, I want you going to my copy or move constructor. I don't want you coming here. So the C++20 requires clause will trigger what is often known as spin-I, but simply says, if you do not satisfy that condition, then this overload will not be available to you. It will not be selected and we'll go off and find a better match. So with that, I can then say, okay, the other thing is, if I'm trying to store this object, well, don't want to be storing references. I want to be storing copies. So if I deduce an L value reference and trying to do a new reference, it will either fail to compile saying you can't do new on references that way, I believe, or otherwise it's going to try to store a copy of the reference, which is not the copy of the object we want. So to simplify the code, this is what I'm doing. I create a simple type def store type that says, yeah, I'm storing the type that you gave me, not without all its reference qualifiers and so forth. And I'm going to forward to it as an L or an R value, so I can take advantage of move semantics if you're moving into me, the object that you gave me. So this will now correctly store the right object, and it will not interfere with the copy and move constructor. Yay. And in practice, what we want to call here, and what the standard specifies, is standard decay T, that in addition to removing the CV reference qualifiers, will also decay functions to function pointers, so we can store function pointers intuitively, but it also decays arrays to pointers to their first element. So if we try to store an array in any object, what's going to happen is it's going to decay the array to a pointer, store a copy of the pointer, and it has, so you've now effectively got a reference to the array, and that can easily become a dangling pointer, a dead reference, because while you thought you had a copy of that array and passed your any around long after the lifetime of the original array, all you actually had was a pointer to it. And there's no easy warning or anything we can do to detect this. The interface is kind of frozen now, so it's not going to be an easy thing to fix if we wanted to. So yes, that's a heads up for a warning in some of the issues of you can encounter. It's probably the thorniest corner case I'm aware of when working with standard any. So we have an implementation. It correctly allocates a copy of the object for us. Yay! And we run it, and the program is fine. I happen to be aware that we've got memory leaks because we never tried to destroy any of those objects. But our test driver here is not particularly going to show that. And at this point, normally I would cut out and I would have some kind of test type that would track when it's been created, destroyed, so I could track lifetimes and spot the memory allocations. But this talk doesn't have time for all that. So I'm just going to go off and fix the bug that I'm going to claim this particular test driver has alerted me to, although there's nothing specifically saying I have a leak here. The conveniences of trying to do a talk in 90 minutes. So the problem I have is I'm holding onto a void star, but I can't delete a void star. I need to delete whatever the type of object that was stored there was. So what I'm going to do, I'm going to create this helper function. This is not a member function. This is just a regular free function out in the same namespace, or appropriately hidden somewhere, so that I can just access it as a regular function that will do the delete for me. It's a class template, so even though all I do is pass in a void star, as long as I specify the angle t to say do delete of int, do delete angle int, it will then be the correct deleter for the type of object I have stored. And because the deleter knows the type, it can safely cast that void star p to be the type it knows it's supposed to delete. So this function now will do the correct thing. All I have to do now is hook this function into my any implementation. So I'm going to, again, I like my type dest for function types. So using deleter is a void function that takes a void star argument. I'm now going to store the deleter as one of my data members. So when my destructor runs or whatever, I can run the correct deleter. And as long as I stored the correct deleter when the object is created, I know it's going to successfully destroy the object correctly. And here we have a quick update to our constructor as the argument's coming in. It takes the deleter member and says, okay, take the address of that do delete function, that template function, and I pass the angle t at the time I take the address, so I get the address of the right instantiation of that function template. Likewise, when the destructor runs, if I have the deleter, I call the deleter with d under data. If I don't have the if d under deleter there, my default constructor doesn't have a deleter function, and I would be trying to call through that null pointer, bad things happen. Whether or not I want to say I ran my test driver through and saw that occur before I went to put the protection in a true test-driven manner, but we saw that one coming, so we put in the quick test for the deleter. And at this point, because we're relying on the implicit copy and move constructors, our program does go bang at us and tell us, hey, you're trying to free this memory twice. It is now trying to do 2 deletes of the pointer. Why am I doing that? Sorry, because when I make the copy of y in z, that copy constructor is just copying the pointer value and the deleter, so it's got the right deleter to run. It just doesn't know that the pointer it's pointing to has already been destroyed. Well, actually, it's y that's going to go bang because you destroy the reverse of the order of construction, but the point is the same. So it's time to solve the problem of how do we copy a standard any when we don't ourselves know what type is stored in it from the outside world. Well, same principle. We're going to have another function template. I'm going to make copy. I pass in the void star to say, this is what my standard any is holding. and I'm going to return a copy of whatever that points to. My contract says, if I'm calling this function, I better have something I'm pointing to, because I can't copy through a null pointer. So I put my assert there just to check my precondition, and I return a new pointer pointing to a new t, where again I do this static cast trick to say, I know I'm pointing to something of type t, I'll cast to it and then dereference that pointer to make sure I get the right copy constructor call. Specifically, this is a copy. I'm not going to try to do anything clever to try to say, oh, can I optimize this with loops or anything? That doesn't happen in any world. So here's our simple implementation. We now have another type def, a duplicator function that says, if I've got a duplicator function, I'm going to go and run that duplicator function on my other data. And boom, I get a clone, and I'm pointing at the right thing, and it's now independent of the any I copied from, so that both our A's can safely run their destructors. All is good with the world. And similarly, I will implement the move constructor. And the move constructor is no except, because it's not going to it's not going to allocate memory. It's not going to copy any objects other than pointers. There's nothing in here that's going to throw, and that's a guarantee that move constructors in general really like. So we're going to put a no except declaration on there, and rather than calling any of our funky clone functions, we're going to call standard exchange, which is my happy way to say, I'm going to take the value of whatever pointer other data has and replace it with null. So it's just a nice one-liner rather than doing 2 or 3 little features around here. Standard exchange was added in C++ 14, and you'll probably see it in a few more slides here. So we go back and run our test. All those original any x, y, z are now passing, but now I've got my move constructor. I just better make sure that's running as well. And just for completion, because we're going to want our test driver to have any chance to expose bugs, now that I've moved from Z, let's try and make a copy of it. And that's crashing for some reason. Despite the fact of having, done my move and everything so on and forth apparently correctly, but, well, I was only taking care of the data pointer. I was letting these other pointers sit around with whatever value they had because they weren't relevant to me when I was in the empty state, or so I thought. But it turns out it does matter now when I make that copy. So rather than testing for whether or not I have a duplicator pointer, I could pay to delete out all these extra pointers, but why pay for the extra throughput? I'm just going to use whether or not I have a data pointer as my gate to say there's some work to do. If data is null, I don't trust any of my delete functions or anything else. If data is non-null, they have to be correct. So with that convention, just simply testing on other data rather than dealing with the duplicator member, this will now work correctly. And this is the notion of implement, test, or test, implement, test, implement, test, implement. But we do need to get through to the end of the interface, and then we can start looking at some of the other implementations. So I'm just going to move on at this point. The next operation we're going to look at is copy assignment. The assignment operator is going to be implemented in the traditional copy swap idiom. We're going to make a copy of the incoming object. Our copy constructor already does all the right things for us, so we don't need to try to regurgitate that logic. Let's just use what we've already tested and know works correctly. And once we've got that temporary copy, we're going to swap with this. So this being whatever state this was in, whatever object it's holding, that will now be destroyed when the temporary object goes away. And again, we just return back our reference to this object. If we think, now moving ahead to the move assignment operator, works exactly the same way. All we need to do is now make the copy, rather than make a copy, we move construct into the temporary, and it has the correct same behavior. None of these are going to allocate. and we end up with the correct state that we were looking for. And finally, I try to assign in any other value, so I pass a string or something, or even pass another int. What we're going to do, we never assign through to the object that's being stored dynamically, even if the types match. We're always going to do this destroy and create, or in this case, make the temporary, do the swap, and let the old value then get destroyed as the temporary leaves scope. So assignability is not a property that's necessary for anything you're going to store into an any, because when you assign the same type, it's still going to do the destroy the existing object and replace it with a newly constructed object. We're not going through the assignment operator. So, moving on to the rest of the interface, there are a couple of modifiers that we had. We had the reset function. That again, if we check for our data member, we can then run the delete and say, yep, I have something, I'd better destroy it. And I'm missing my line that then resets d under data to null. It was there in my implementation, but I must have fixed it after the slide where this was not supposed to be exposing a bug. But yes, there is a missing line that resets d under data to null putter. And likewise, the swap function will member-wise swap each of the different members. And naturally, that you're swapping pointers. It's cheap, it's efficient, it just does the right thing. But the key question is, now we've got all our data stored in our any objects, how do we get it back out? Well, ultimately, we're going to have to guess at the correct type that's stored inside, because otherwise we can't, where are we going to put it? If we're not putting it into something that's got the right type, it's not going to work. And if it's going to come out as the right type, we've got to make our guess. But typically, we're going to have some kind, you're going to set up the system in such a way you've got a good idea what that type is without having to go and query every type under the sun to say, do you have an int, do you have a double, do you have this, do you have that, do you have a type I never thought of, but I'm just thinking, no. Now, we have some external information. Often, for example, I might have a map with key value pairs where the key tells me what kind of value is stored in the any. And that lets me store a wide variety of different types in the same map, as opposed to having different maps for different values and then trying to correlate when the keys providing the ordering and the lookup. I don't want those put across lots of different maps. So this is one of those places where any is a nice part of your data structures. Perhaps the contract you have with your API saying passing through system boundary layers and passing these objects as an any, there can be one of a variety of different types that the client at the other end, from the context of the API, will know, okay, I unpack the any as this kind if I've got these arguments, this other kind if I've got these other arguments. So the receiver of the API knows how to unpack the any just by the nature of the contract, and we don't need to keep going to write lots of code to tell us what we already know, although trust but verify. This is where we have the type function. And if I call the type member, it will return the standard type info of the object that's stored in the any. And if the any object is empty, it will return the type info of void. So even the empty case is handled, but I can't store objects with type void, so there's no risk of confusion with something that might be stored in there one day, unless some folks do get their regular void type into the library, I guess, but language even. But that's something not happening as of C++ 23. So how do we implement our final accessor, the type function? Well, fairly simple. I add yet another data member to my class that stores a pointer to the type info. Type ID returns a reference. I could just store the reference, but if I store the reference directly, then my any implementation would not be copy assignable, because when I assign to my any, I can't replace that, rebind that reference. So we're storing a pointer, which means it might be null, but what we do, given that we never want the int type to be null, we're going to default it, in our data member initializers, default member initializers, we're going to give it the address that I get from type ID void. And when I call the type function, which returns by reference, not by pointer, I'm just going to dereference D under type because we have a guarantee this is never going to be null in our system. So there's no risk of dereferencing a null pointer there. Or if we are dereferencing a null pointer there, the bug is in our implementation and not in the user giving us bad data. Hence, we're going to test and expose any such bugs. So quickly run our test just to demonstrate how the feature works. I'll create an A does not have a value. I check the type ID of A, and it is indeed type ID of void. Similarly, I put an int in there, and I check the type ID because the literal type is of type int. Then B's type is type ID int. If I assign B to A, I make a copy of that int. I therefore need to update my internal pointer to say, yes, I'm now pointing at an int. And when I query the type info from a.type, it comes back and tells me, yeah, you've got an int in there. Congratulations. How do we actually get that int back out, though? Nothing in the public interface we've seen actually tells me how to get access to the int. And we get to it actually with a facility called Anycast. This is a free function template modeled after dynamic cast, you can see in the name. And the idioms are fairly simple as well. If I pass an any star to the argument, and the type I'm trying to cast it to is not the type it stores, then I'm going to get a null pointer just like I would if I tried to dynamic cast to the wrong type. And this API never throws. On the other hand, if I pass Anycast a reference to any, and I've guessed wrong, I'm going to get a bad Anycast error coming out. And when I say I guessed wrong, that means I guessed at the base class when you're storing a derived or vice versa. There's no conversion check there, no base to derived conversion either. It's simply you guess the exact right type so you can pull that out, or you don't. And an implementation of this interface, because it's a free function interface and there's nothing we've seen in the public interface, gives it access, would use friendship. But just to make our code a bit simpler and not have all these forward declarations of friends and things that are horrible to track down, I'm going to hack it with an undocumented public accessor that I'm just going to call private access. And private access simply returns the pointer to the D under data member. So how do we implement Anycast? Which is the last part of our interface before we actually completed our any. Well, if I've got a pointer or a constant pointer coming in, so I've got to provide both overloads. If the operand is not null, and we're going to take advantage of short circuiting here so I can get a single if statement, and the type ID does match the operand's type, then I know what's in there. Congratulations. So I can cast to the correct pointer type. Or I can take my private access to get the void star out and static cast it as my return value of the correct type. And if condition fails, I return null pointer because you didn't guess right. Or especially if you didn't guess right from holding nothing. Similarly, if we have the same overload just with the non-const, so if I get the non-const pointer back, I can directly manipulate the value that is stored in the any because I've got a pointer directly to that data. So I can manipulate that copy of the original, and it's not going to change the original. We've made a copy, but that copy is not immutable because I can get modifiable access through this pointer and therefore hack away at however I want to update that original value. More likely, though, is I'm going to go through, if I want to change the value, I'm going to go through Anycast to a reference. And again, you'll notice that the interface has template class T and the any coming in by reference, and it returns T. So if I ask for return by value, I'm going to get back a value. But the intent is that when you instantiate this, you'll do Anycast angle brackets Tref to say I want back a reference to it, or const Tref to say I want to have a const reference to the held object. And the implementation here is relatively simple. Again, because T is expected to be a reference type, we want to unreference it. So we can have a type def to do that. We're going to call the Anycast to the that returns pointers from our operand, and if that succeeds, yeah, I can just dereference that and return it. And if that test fails, well, the API says throw a bad Anycast exception. This is like bad cast on when you try to dynamic cast a reference to the wrong type. That any type is going to throw bad Anycast, which is derived straight from the standard exception. It's not in the hierarchy of the runtime errors and the logic errors. It's just a straight, cheap, simple exception object. And we have the same overload again for the regular reference, the non-const reference. Now, so this is more typically how you probably assign to the value that's stored in the any if you're confident in your guess. And if you go back and look at that interface, when we wanted to use the pointer interface to extract the pointer, go back a slide, you'll spot that when I call, I'm trying to look at my code now. Yes. Because I went back 2 slides. That's I knew something was fooling me. When I do the Anycast here, you'll spot I'm Anycasting to unref, not unref star. The star is implicit in that I'm passing a pointer, so I don't need to double up by saying pointer again. So unlike dynamic cast, where you would cast to the pointer to get the pointer, here you specifically drop the star. It's just you cast to the type you're expecting, and you get a pointer to that type back out. Again, to extract a reference, you need to pass out a tref or trefref. Otherwise, you're going to actually get a copy returned back, because that's what you asked for. You said, please give me that copy, and it will be constructed directly in this Anycast. When you return star p, it's going to, at that point, it's then going to make a copy, because that's what we've declared we're returning. And it will not even move optimize. So here's our test. Int star p is my Anycast from my pointer, and go, yeah. If I dereference that pointer, I've got the value I expected. And likewise, if I look at the A that I copied from B, it too also has its own copy of 5. So that's our basic implementation of Any. I have no questions. Does anybody have any questions before I jump into the alternative approaches I was going to consider? Got about 35 minutes left, so luckily the bulk of this presentation is the original implementation, because most of what we're going to see is intuitive once you've made the basic simple quick changes that come in. My first concern, the footprint of my Any object is much larger than it needs to be at 4 pointers. You may argue that 4 pointers is not a lot of data, but it's 4 times as much as I really need. What I want to do is hoist all those function pointers and so forth into the same place that I'm storing the value. So that way I only need a single pointer. So I'm going to create a base class that I can query those functions through, which will be a pure abstract base class. It's going to have a default constructor, destructor, it does the right thing. I'm going to have pure abstract functions called clone and type, that will respectively clone the object and tell me what type it is. I don't need the equivalent of the delete, because that's going to be the destructor. And again, you'll spot these are all safely encapsulated within the Any class itself. These are it's member classes. I don't need to expose them to the outside world. So we're going to have an owned object. It's final, because might as well take whatever opportunities we get for devirtualization. And it's going to have a constructor that says when I store a value, I'm going to store a copy of my value directly in the object, because I'm going to dynamically allocate my owned object. it can happily pay for the storage of the supplied value. So that's what my constructor is going to do. Likewise, when I implement the two virtual functions, clone simply says return. I don't have any funky casting to do now because I now have all that in my owned object, because my owned object is a template. It's a member template in this case. So I can just return my copy constructor. Oh yes, I'm looking at this the end of anything. Have I failed to dereference a pointer? But of course, in the owned object, the end of value is not a pointer. It's just the value that's stored in place. Likewise, if I want to find the type info, well, it's type ID of my template parameter. I have nothing else to examine. As I said, the destructor is going to do the correct thing to destroy my object. And I'm going to add, as we're going to see later, this address function that just returns the address of that GL value, the D value. And because D value can be any arbitrary type that users might be perverse and go and overload their address of operator just to throw us off, we're going to use a standard library facility standard address of to make sure that even if people throw us awkward objects, we return the correct address. Now, the implementation of my any, rather than having 4 distinct pointers, has just the one. The NWP is my, which again I'm going to default member initialize to nullpater, is going to do all my heavy lifting. If I want to simplify simplified implementation of my value constructor here, I simply initialize dimple p with a new owned object of t and forward the appropriate argument. That will again forward the L value and R valueness of the t object. Likewise, the destructor for any and the reset function in turn simply delete the dimple p, and because that's got a virtual destructor, that will call the correct destructor and release the stored the undervalue within the owned object. So this seems much simpler to me. The copy and the move constructor. Same deal. For the move constructor, I'm going to do the exchange of the input pointers with a null. And for the copy constructor, that's where the clone function comes in. Now, if I'm going to call clone, I'd better make sure that the other actually has an impl. So even though I like to do all my things in one line where I can, just to not have too much state messing about, so I've got my ternary here that says, if you have a value, clone it. Otherwise, you don't have a value. The assignment operator. I've not gone with the any swap on this one. I've just gone with the more direct, just because why pay the extra operations when I don't need them. I delete the impl p, which is guaranteed to succeed. I then exchange with the RHS, the impl p with a nullpater, and I return. So RHS now is holding null. I'm holding whatever RHS held, and there were no temporary objects to mess about with this time. On the copy assignment operator, though, we're back to the old world because making those clones and things is not something you're going to want to manipulate by hand. There's no good reason to break the encapsulation by that. The type info function. Now, again, it has to check if impl p is there. And if it's there, I can then call the type function, and otherwise I return type ID of void as before. The Anycast is now actually going to literally take advantage of the dynamic cast that was designed as that inspired the interface. So we're actually going to dynamic cast to the owned object t star because dynamic cast does want the pointer there. And it's either going to, I'm going to have a wrapper that either says, yes, the dynamic cast succeeded, or I'm going to pass it an operand that says, I've either got an operand, or in which case I'll give it to you, or I'm going to return the nullpater. If we return the nullpater, the if clause fails and we jump straight through to the return. But assuming I've actually got something, that's where that address function I showed earlier came in, I've dynamic cast to the owned object of T. I didn't try to get the T out of it yet. And the wrapper has that address function that, if I just jump back, here we go. The address function simply returns the address of this value. So jumping backwards and forwards, I'm hoping that's clearer and not confused people. I don't think I described that one too well. Second concern that occurred to me at this point is branches. There's still a few places where we need to check whether the data or the import is null before we can go off and perform the operation. So again, this is true to both the implementations we looked at and potentially other implementations that you'd be thinking of. And this can then be resolved with what's known as the null object pattern. With the null object pattern, rather than storing null and having to treat null as a special case, you create an object, with the same dynamic type that will work through our system, that will behave correctly when the object is not holding anything. So if I were to think in terms of an owned object, I would potentially have a specialization for void, so that, where's my owned object? Sorry, I'm fooling myself jumping through my slides too quickly. This is what I have to, okay. So over here, if I've got a specialization for owned object of void, that would then return type ID correctly. The clone object, the clone function, would always return the null pointer, or not return the null pointer. It would return another cloned void object, but you've got what you're storing is a void star. So there is actually no storage for the void star. You're just returning a pointer that's to the object itself that's void. And that's what the address function would be specialized to return. It will return just an appropriate null pointer or variation, so that as you go through your interface to say, I'm coming through the public interface now to get access to this, it's going to fail in exactly the same way that we were reporting the failure when we queried and then took the alternative action. It's just the alternative action is now built into the owned object itself, or into your function pointers, or whatever your null object state for the different internal representations you might have been choosing. So given there's a variety of implementation choices you have here, I don't have slides illustrating the null object pattern, because I figured by the time I was getting here to be too late to dive into another full implementation. But the notion is you store the null object, you don't branch, you call, and it dispatches to the correct operation. And in the case of the owned object implementation we were looking at before, you're going to dynamically allocate one of these, but that now means that you might have to dynamically allocate for your move from state and your default constructed state, and that's a problem. In which case, you might try and store your null object as in static storage somewhere else. We've just got a global object because this thing's stateless. It doesn't do anything. There's going to be no data races dealing with it. So I can have all these different any objects in their empty state, all pointing to the same null object. But now I've got to be careful when I destroy the any, that if it's pointing to the null object, I don't actually run the destructor. So I possibly have a destroy function as one of my other virtual functions that is responsible for either delete this if I don't have the null object, and the null object just treats that as a null operation. So there's a variety of extra ways and concerns, and some things simplify, some things become more complicated. So that's where I was really looking to get some information out of the benchmarking that I don't have the results on yet, I'm afraid. Another popular concern to address is excessive allocations. An int is about the same size as a pointer. It might even be half the size of a pointer. And there's a lot of commonly used objects that are really quite small. And it seems excessive to pay for a trip out to the memory allocation and back, especially to the global heap, for a lot of these small objects. So there's a variety of techniques where I can store some kind of internal union or buffer that says, if my object is small enough, I'm going to store it directly in the footprint of the any. But now I've got to somehow store either a virtual table or a manually constructed table of pointers to provide the information to say this is how I do the clone and I do the delete and do these other operations. Otherwise, I'm going to dynamically allocate as before. And again, we're back with the null object where if the thing itself is not dynamically allocated, you very much are in the case of now I do need to have a system to say I do not delete this pointer because the object's actually stored internally, along with this other reference of pointers or virtual functions that gave me access to the behavior. One of the issues that comes with this is because we want all our move constructors and move assignments to be no except, we can't store a small object that does not itself have no except, move construction, and move assignment. Actually, move assignment doesn't matter because when we do move assignment, we're doing the move construction again. So, but it must have a no except move constructor, or else it should not qualify as a candidate that we would store in our small representation. One of the interesting optimization choices that comes up at this point is I might choose deliberately to make my any footprint larger in order to store more small objects. There are some implementations, standard string, for example, that rely on the short buffer optimization that says I can store my string if it's super short string in the same representation that would otherwise store all the bookkeeping for the dynamically allocated memory. We might well make that larger because short strings, up to a certain, maybe for a part of your source code and you know what's good for your environment, you might find there's a short string size that's more appropriate than the smallest possible because saving memory allocations can be a really big win. And this is, again, another popular thing to do with standard function, which is another type erasing kind like standard any that will often have a larger footprint than just to store a single type erase pointer. In particular, we want standard function to be able to store pointers to members, which are often 2 or 3 pointers in size, but trivial. And we want a footprint large enough to store those types and guarantee that those work without going off to the heap, potentially now throwing exceptions. So there's interesting value in going for the small object optimization, but we now do have to correctly handle the idea that sometimes I've got an object in my footprint that I don't destroy, and sometimes I have it dynamically allocated where I have to. Or don't delete, so I have to destroy it, but I don't have to delete the memory because the memory is my footprint. And at this point, there's a couple of other implementation ideas about what to describe there, where I can replace the virtual functions with a manually coded up table of pointers, kind of like we saw in the first any, but I can move, because that set of pointers is the same for any object of that type. I can just move that whole table of pointers off into static storage somewhere and just point to the appropriate table, kind of like storing a vtable pointer of my own. So I can effectively implement my own virtual dispatch. When I'm doing the embedded implementation, I might use an any sort of union, or I might use a well-aligned array, or there's, again, a variety of different ideas here. So all these ideas are fairly independent of each other. And therefore you can mix and match as you try to seek out your optimal implementation of any, or you might profile and benchmark and find that for all the work you put in, it doesn't actually matter that much. As I said, I didn't get out the far end of my benchmarking yet. I don't have results to share one way or the other, so it's still a fairly open topic for me. And again, I've described some of my strategies for implementing standard any. You may well have ideas of your own. But The other thing I wanted to briefly mention is once you start getting down the rabbit hole, you then start thinking, what else could we have done that would improve the use of standard any? Because as I say, the design dates back to 2001 and the language has moved on a long way. Well, C++20 now, for example, supports constexpr allocation. So how much of the any interface could we try to render constexpr? I'm not looking for a use case. This is just an interesting experiment in what you can or can't do with the code. C++20 now guarantees we can do virtual dynamic dispatch in constexpr, so that's not a problem. However, even though I can get my type ID and type ID works constexpr, the comparison operator on type info, if I'm using that, does not work as constexpr in C++20, although we have already made that change to the C++23 library, so that route is still open. If I was going to be comparing type info directly route in my implementation, I found that comparing pointer values seemed to work in constexpr. I'm not sure if it was guaranteed to behave or was just getting lucky, but in theory, you don't want to have multiple type info objects representing the same type in your system. I don't know where you end up with shared objects, though I was never in that kind of an environment. But the interesting thing as you're playing with constexpr is some of your options for implementation strategies start getting ruled out because constexpr is still a moderately restricted language facility. There's things you can do with it, there's things you can't. Trying to manage and access my data when it was in a well-aligned array versus when it was in a union had different issues. If I'm trying to generate my own vtable by storing function pointers, I don't believe I can dereference those correctly in a constexpr function. Whereas if I go with the virtual function and let the compiler take care of it, that is going to work. So you start looking at, if I want to migrate what I've got today to a potential constexpr future, the strategy I chose to implement today might have implications as to whether or not that's something I can do without breaking ABI and changing the layout and doing a variety of other things. So again, that's one reason looking ahead can help. You can pick a solution that's not binding you into too specific a direction. And the other one, surprise, surprise, I was taking a look at was Pmr Allocators. And the idea here is clearly I can't store the allocator in the footprint of the objects we were just looking at. So it would be a distinct type from standard any. I have no idea whether we'll be proposing this. This again was just, I'm the allocator guy, so I'm going to see what it takes to actually make an allocator enabled any. The principle of the Pmr Allocator is that it's set at construction time. So when I create my standard any object, I provide it an allocator. And then when I assign and replace or do anything else with this any object, any of the objects I try to store in there, if they're allocator aware, will use the same allocator that's already in any object. It will never rebind to the allocator of the values of the objects coming in. This is important when you've got containers and so forth, that lots of assumptions are that all the elements in the container have the same element as the container, so that I'm safe to run algorithms over the sequences where I might swap and exchange elements. And in those cases, you want to be sure all the allocators are the same. So that's built into the Pmr model. But it does mean now that my any object has to store an allocator even when the object, the value it's holding, does not use allocators, or indeed it's empty. So as I said, it's not an ABI compatible extension. We put it into its own space. Largely seemed to be working for me until I got to trying to add constexpr support for my Pmr allocators, which came tantalizingly close. But it turns out that there's a little corner that, because the Pmr allocators allocate bytes and then store objects in that range of bytes, the constexpr allocation model requires that you actually allocate and store an object directly into that storage. So you can't do the cast through to say, okay, I had some raw memory and I have in place newed an object in there, even using the construct app library facility that's designed to support that. There's one cast very deep in the depths of this that unfortunately doesn't work through constexpr today without relaxing the language rules here. And I'm not going to push that through any, because that's something when I come back with my allocator work in the future. So, coming back to that vexing question of benchmarking, what did I learn? Well, I learned what everyone already knows. Benchmarking is hard and it takes time to get reliable results. So yes, I don't have those results to share, I'm sorry. Typical concerns that you hit when benchmarking, of course, the accurate timings, that you want to make sure that you run over suitable periods of time where you're not going to be disrupted by other work that's happening on the computer at the same time, or that work suitably averages out because you do sufficient benchmarking. But again, different compilers and different platforms are going to perform differently. So benchmarking on a single platform and on a single machine on that platform is not really a reliable way of benchmarking. So acquiring sufficient different resources with different compilers, different machines, different architectures is part of what I was trying to do here. And again, we get the notion of determining useful loads. If I run a benchmark where I store an int and I'm done, how much has that tested any that is supposed to adapt to all these different types? How many types is standard any likely to see in a typical application or workload? How many times is it going to go through and replace them? Do I need to test it with 10 types, 100 types going through that any object, or just creating 100 different any objects holding different types? Going through different assignment combinations? How do you know when you've determined an appropriate representative load? So that was a concern. I was mostly looking at doing this by just generating workloads with templates that have an instantiate. By passing 100, I have a different 100 different instantiations of that template, so I've got 100 different types. But is that representative, or I'm having 100 types that are very, very similar? So again, getting the useful workloads, large, small objects, and it's interesting. So again, and that's assuming I'm trying to measure one thing, but I have lots of things I wanted to measure. Runtime and memory consumption are the main things that people think about. That we're often template land and C++ headers, so compile time may be a concern. Given I'm memorizing all these different types, different ways of doing that more or less efficiently might impact program size. Whether or not things are more in line or not is going to impact program size. Then you've got how does varying implementation have different impacts at different optimization levels, or raise costs of debug support on different platforms? Do they all optimize it equivalently? I say some platforms might optimize differently even on the same code? So hence the desire to get multiple architectures and multiple compilers. But coming through to this point, I just didn't get my homework finished in time. So hopefully I will have something to say about this. I might try and send the paper to WG21 when I'm done, just a by the way information paper. I do want to get some benchmarking results out, but it's not going to be today. So quick conclusion. What did we learn? Well, TDD can be a great way to get started with your slideware. Be careful that you don't get too hooked and it's not going to go all the way to the end of your talk, or your talk's going to take 2-3 days. But with a simple project and simple code like this, it nicely chunks up the granularity to say, I'm introducing just a new little bit, just a new little bit, and you can see it in use. And it felt nice and intuitive for me getting started until it had served its purpose. But what you didn't see is behind the scenes, I've got all my tests running. So as I'm posting all the other code, it was mostly cut and paste straight from my implementation that I was tested and had confidence in, or knew the bugs it was supposed to be exposing. As I spotted a couple where I only got 1 out of 2 lines and pasted, so that was oops. Another interesting thing is you look at a type like standard any, and there's just a bunch of different questions that you might think, oh, here's a way I can optimize, and here's a way I can tune and tweak. And then you realize that you can actually pull them apart and assemble them in different ways. So hence you get into my cornucopia where it's not just one evolution. This is a nice way to make this more and more and more efficient. It's, there's different forks in the path that, I can combine things in different ways. For a standard library type that's going to be heavily used by many different people, it may well be worth investing the time and investigating your variety of solutions before you pick on any particular final choice. And again, when I start looking at things like constexpr, you run into how implementation choices can restrict your evolution in the future unless the language changes and opens up those choices again. Who would have thought we were going to get constexpr allocation in C++ 20? So the standard may open in the future, but it's nice to implement with an eye looking to the future. And that's about where I'm done. So I'm about 7 minutes early. If anyone has any questions. Otherwise, I think we're done.